Okay, so I say a few words of presentation before the talk. So I'm very happy to welcome Adnan Darwiche for the invited talk of this second session of Gandalf. Adnan got his PhD and master from the Stanford University, and now he is professor at the Computer Science Department at the University of California at Los Angeles, where he directs the Automated Research Group. His research focuses mainly on probabilistic and logical reasoning, both from the practical and the theoretical side. And among the many works that he made in the past, in a recent position paper on the communication of the ICM titled Human Level Intelligence or Animal-like Abilities, he presented a view on what just happened in AI and on the consequences for the scientific community that I found very inspiring. And so for this reason, I invited him to give this talk here at Gandalf. I hope that everybody can appreciate this somehow original view of artificial intelligence from Adnan. Today at Gandalf, he will give a talk on 3 modern roles for logic in AI. So please, Adnan.
Right, thank you, David. And again, thanks for the invitation. Happy to be speaking to this community. So this talk actually has 3 segments. And in the first segment, we'll actually look at how we can systematically use logic to solve problems beyond NP. And in the second segment, we'll look at how we can use logic to learn from a combination of knowledge and data. And the third segment, which is the most recent in my work, is we'll see how we can use logic to actually reason about the behavior of machine learning systems. Now, everything I'm going to be talking about will be in the realm of propositional logic, and in particular, based on the theory of tractable Boolean circuits that I have been working on for a while. So there is a lot more going on the interaction between logic and these subjects beyond what I'll talk about today, but this is more of the things that I've been pursuing and others, of course, following up on. So what I'd like to do initially is just spend 1 slide on each one of these to give an overview before we get into the details. So this is the first segment and the more substantial one, which will also give us the ingredients for the second and third segments as well. And here what we'll see is we have these complexity classes that have a lot of interesting problems in AI. And then we're going to look at 4 problems that come from the world of probabilistic reasoning and machine learning that are complete for these classes and that have been of interest over the decades, and a lot of investments have been spent on. And then we're going to see that there are the prototypical problems for these classes are actually all on Boolean formula. So we look at 4 corresponding problems on Boolean formula that are complete and prototypical for these classes. And then the idea is that we can reduce these problems here to the corresponding one on Boolean formula. But the more interesting thing from a practical point of view is then how do we solve these problems? And then we will see that we can solve all of these problems on the Boolean formula systematically by converting the Boolean formula into tractable Boolean circuits of appropriate types. So the idea, if this compilation is successful, then you can solve these problems in linear time on these circuits. So the big picture then is computationally, the most significant thing here is this compilation process of Boolean formulas into tractable circuits, which gives us a systematic way for solving a lot of problems. And we'll see this is not just theoretical, but actually actual systems are based on that. Now, in the second part, we're going to see also tractable Boolean circuits playing a fundamental role in learning from combination of data and knowledge. So the idea is we're trying to learn a probability distribution, either in a supervised or unsupervised fashion. As you know, probability distribution is defined over a space. And then knowledge, which typically expressed using logic, what it does is basically rules out part of this space and then gives us what we call a structured space or a constrained space. And then data is used to learn a distribution over that reduced or structured space. So we see that if the structured space is represented by a tractable Boolean circuit that facilitates learning and makes actually inference, probabilistic inference tractable on the result. And in the third component, we'll basically see how we can use tractable Boolean circuits also to reason about the behavior of machine learning systems. So the basic idea is today, you typically, a lot of the AI systems or machine learning systems are based on learning classifiers from data. So you have data, you learn a box, could have various forms, could be a Bayesian network, classified, neural network classifier, random forest. But typically these classifiers are discrete in the sense that the input is discrete and the output is discrete. The input is an instance, the output is typically a decision. And then we'll see we can actually compile the input-output behavior of that box into a tractable circuit. And once we do, then we can use the theory of tractable circuits to actually answer questions that our people are interested in today, like explaining decisions, measuring the robustness, and so on. And most of these problems are actually beyond NP, which again are facilitated by this compilation process. And let me say that I've given this talk twice this summer in the form of tutorials. One of them was an hour and a half, the other was 2 hours. So this is somewhat abbreviated version, but towards the end, I'm gonna give you a pointer to my YouTube channel, which has a lot of videos that elaborate on some of the things that I will go over. So let me start with the first segment now, and let's go back to the main ingredients that will make this segment. So what we're gonna do is, I'm going to start initially by showing you these 4 problems that I mentioned from probabilistic reasoning, and then we'll look at the 4 problems on Boolean formula. We'll look at an example reduction, and then we'll talk about tractable Boolean circuit, and we see how that allows us to solve all of these things in a systematic fashion. So I'll illustrate these probabilistic problems and problems from machine learning based on what's known as Bayesian networks. They're certain types of probabilistic models. They have 2 ingredients, a graph like this, directed acyclic graph. This is about a condition that a person may have, which can be tested by 2 tests. The condition depends on gender. And this variable here represents whether the 2 tests are the same. Sometimes I want to say that the 2 tests came out the same, but I don't want to tell you whether they both came out positive or negative. The goal of this model is to specify a specific distribution. The topology of this Bayesian network has a particular interpretation in terms of conditional independence between the variables, but we're not going to go over these. And those independence constraints do not pin down the distribution. You also need to specify these numbers here, which effectively for every variable like this guy, we need to specify the distribution over that variable conditioned on every state of its parents. In this case, there's only one parent S. So this is done by this table here. You can see this table has 2 distributions, each conditioned on gender, and similarly for the other variables. So the constraints, independence constraints and implied by the graph and these numbers pin down a unique distribution, and the queries are with respect to that distribution. So we're gonna look at 4 queries. Here they are. I'm gonna show you the decision version of them or illustrate them concretely. And here's the first one. Here's the actual model, and this query is NP-complete, the decision version of it. It's known as the most probable explanation on MPE. And the idea here is that, let's say I come and tell you someone did the 2 tests and they came out to be the same. This is indicated here. Now I have 4 variables left, and each has 2 states. So that's 16 states, and I'm interested in the one that has the highest probability. That's basically the MPE query. And you can see the answer here. It happens to be basically a female doesn't have the condition, both tests came out negative. So this is the MPE query. And and it's NP-complete decision version. The next one, which is the very common, is known as the marginals. And here where I'm basically trying to compute the marginal distributions over the variables. All right, so someone tested positive for both. and there is 45% chance they have the condition. That's what I'm trying to compute, all right? So this is the marginal query. And so we're moving up in difficulty here. The next one is known as the map query. It's NP to the PP-complete, and this is similar to the MPE, but instead of optimizing over all variables, the user get to choose the variables that we want to optimize over. And in this case, the user chose gender and the condition, and I'm trying to find the most likely state of these two variables, and it happens to be that. It's interesting that if I optimize over all variables, it's only NP complete, but if I optimize over a subset, it ends up being a lot more difficult. And this has to do with the fact that in probabilistic reasoning, computing the probability of a full variable instantiation is pretty easy, but computing the probability of a partial instantiation is actually more difficult. And by the way, these screenshots are from a system from my group known as SAM-IM. It's available online. It's very heavily used. I think maybe at least 60, 70,000 downloads at this point. Okay, let's get to the last query here and the most difficult. And let me say that these three queries that I just mentioned, very common. They're actually been around for decades. They're even in Yuda Pearl's book from the 80s on Bayesian networks and probabilistic reasoning. The next one is more recent, and it's representatives of computing expectations. It's known as the same decision probability. We introduced this about 10 years ago. And let me explain this. So here's a Bayesian network model. And as people may know, these models are typically used as classifiers, meaning you give me test results. So this is a model for detecting pregnancy based on 3 tests: blood, urine, and scanning. So what happens here is you typically give me an instantiation of these test results, and then you compute the posterior on pregnancy, and then you check the probability against a threshold to decide whether it's pregnant or not, yes or no. So in this case, the threshold is 0.9. And given that this is the only thing I know, probability is this, below the threshold, the decision is no. So what is this query? The query, again, the user picks variables. In this case, he's picking these 2 tests. And you want to know what is the probability that this decision will stick, will remain the same even after observing these 2 variables. So it's kind of an expectation over a decision. And in this case, the SDP, or the same decision probability, is 78.7. So about 79% probability that the decision will be the same, no pregnancy, if you go ahead and collect these 2 test results. It's kind of a value of information query, and this is the most difficult of the queries we're going to look at. There are related ones to this, again, all kind of value of information, which are PP to the PP complete. Now, what we're going to do now is look at the corresponding problems that are prototypical for these classes, which, as I mentioned, they're all problems on Boolean formula. Some of them are very common and well known, and some are maybe less known. So we'll walk over these. And the first one is, of course, SAT. Everybody knows that. I have a Boolean formula. There is a number of instantiations, and the question is simply, is there an instantiation that satisfies the formula? And the answer here is yes. And as we know, this is NP complete. The next query is basically what's known as MAJ-SAT. And in this case, I'm not just interested in whether one of these instantiations is satisfying. I want to know if the majority of instantiations are satisfying. So here I'm starting to do counting, basically. And it happens that the answer is no. In this case, there's only 3 out of 8 that satisfy. And now we go to the next 2, which are more difficult. And both of these problems, the one that are coming up, we have to actually split the variables of the Boolean formula. So part of the input is a Boolean formula plus a split of the variables. So now we're looking at MAJ-SAT, which is NP to the PP complete. And here I have the Boolean formula, but I decided to split my variables into X and Y like this. And the query is the following. Is there an instantiation of the X variables under which the majority of Y instantiation is satisfying? All right, so the answer is yes, because in this case, if you fix C to false, there are 4 instantiations over the remaining variables A, B, that is Y. And the majority of these actually satisfy, 3 out of 4 actually satisfy the formula. So you can see why this is basically NP to the PP. It's basically like NP I'm searching for in an exponential space. But if I show you one candidate and I say, is this the guy you're looking for? In that case, you have to solve a PP query to decide that. Now you can imagine what the next one is going to be, which is the PP to the PP. This is basically MAJ-SAT. And in this case, I'm saying, are the majority of X instantiations such that under each one of these, the majority of Y instantiations are satisfying, all right? So I'm basically counting, but if I show you a candidate and I say, should we count that candidate, then you have to go and solve another counting problem to do that. So these are basically the problems that are prototypical and complete for these. And before I move on, I want to show you two variants on the MAJ-SAT problem, which are the ones that get used in practice. And in fact, we're going to do the reduction for one of them. And this is known as model counting or sharp SAT, which is the functional version of MAJ-SAT. I'm basically, I want to count how many satisfying assignments. I want the number 3, not just a yes, no answer. And the other variant, which is even more practical, is what's known as weighted model counting, right? So in this case, I have weights attached to these satisfying assignments, and I don't want to just count the satisfying assignments. I want to add up their weights. So in this case, I want you to produce this answer, which is the result of adding these 3 numbers. Now, how do I get these weights? Because I have an exponential number of these, I'm not going to specify an exponential number of weights. What happens here is you assign a weight for every variable instantiation, single variable, all right? So you can see here, I have these weights. So for the variable A, the weight is this. For the literal not A, the weight is that. And then the weight of a variable instantiation is simply the product of the corresponding weights. So this way, I can specify this exponential number of weights using a linear number of weights of this type. And that's basically the weighted model counting. It's receiving a lot of attention now, and you'll see why in just a second when we actually look next at the reduction. So if you look at the picture now, we have these complexity classes, pretty rich, have a lot of interesting problems, and we have the complete ones based on Boolean formula, and we have the ones that come from probabilistic reasoning and machine learning. And let me show you very quickly one of the reductions. This is a vanilla-based reduction, but just give you the gist of tying the probabilistic and logical world. The ones that are used in practice are more sophisticated versions of this one. What we have here is a Bayesian network of the 3 variables. And you remember, we have to quantify it by these probabilities. I'm not showing them in tabular form here, but we need 2 distributions for B, one conditioned on A true, one conditioned on A false. These are these numbers, which are known as parameters. Similarly, for this guy, I just need a distribution over A, which is these 2 numbers. Now, if you look at the distribution that is specified by this Bayesian network, it looks like this. For every variable instantiation, you have these parameters that are probabilities but multiplied. There's 3 of them, and there's 3 because there are 3 variables. And in fact, if you look at the 3 variables, the 3 parameters, we're picking one from each set. We're picking one from here, one from here, one from there, and we pick the ones that are compatible with the variable instantiation. It's pretty straightforward. Now, why is that the case? That's another story. We're not getting into the details of Bayesian networks, but that's what is the distribution that's specified by Bayesian network. And the reduction here turns out to be pretty simple. We're going to reduce the computation of marginal probabilities on this Bayesian network to weighted model counting. And it's pretty simple in this case, especially that these variables are binary, but it still works in general with some modifications if the variables are multi-valued. We use the Boolean formula we're going to have will have the same variables as ABC as Boolean. We're just going to introduce one more type of variable, Boolean variable, for each one of these numbers. And it kind of represents the presence or unpresence of that number in a particular variable instantiation. So here's the Boolean formula. It's pretty simple. For every one of these parameters, I have a sentence that looks like this. It says A is true and B is true if and only if this parameter is present. These are the new Boolean variables that we introduce. The main point about this reduction, as you can see, this is efficient. and it's pretty straightforward. The only thing we need to do now is give weights to the different variables so that we can have a weighted model counting problem, and that turns out to be also easy. All of the variables in the Bayesian networks and their negations get weight of 1. For these new variables that we introduced, the negative version gets 1, and the only guys that get real numbers are these guys. The positive literal gets these numbers. These are the probabilities from the Bayesian network, and that's basically it. So this reduction or this Boolean formula has the property that it has exactly 8 models, which correspond to these rows in this table. And let's look at one of them. Here's one model of this Boolean formula, which correspond to the second row. So you can see here A true, B true, C false. Now look at all of these guys. What happens by construction, the only variables that appear positively among these are the ones that correspond to these 3 values here, these parameters, and everything else appears negatively. So if you actually compute the weight of this variable instantiation, you get this, which is exactly what we want. And if we call this yellow or this Boolean formula big delta, and I'm trying to compute the probability of an event, small delta, then that ends up being just the weighted model count of this formula. That's basically it. And as I said, this is a pretty vanilla flavored version reduction. This is not just a theoretical exercise. Systems are based on that. Some of them have won competitions. This is an example of one of the competitions run by the conference known as Uncertainty and Artificial Intelligence Conference, UAI. The system ACE that is built based on these reductions, you can see actually solve these problems. The only one that solved these problems in this case. This pretty typically is quite effective when your probabilistic models have massive logical constraints in the form of 0-1 probabilities. These kind of reductions are now common in areas where there is no tradition of building algorithms for a long time. They're pretty commonplace in probabilistic programming, and as I said, more sophisticated reductions are being used there. So this is the big picture, and where we're leading with all of this is that you basically, if you know how to solve these prototypical problems efficiently, we have these efficient reductions, then basically you have a systematic approach for tackling problems here. And that's happening in practice. The key thing now is, how do I solve these problems? And this is where the interesting part comes in. Although there are dedicated algorithms to solve these problems, we're going to look at a unified approach that reduces that to a problem of what's known as compilation, where we compile these Boolean formulas into tractable circuits. That's going to be our main machinery or computational machinery. So basically, we're going to look now at the tractable Boolean circuit next. And again, the idea is, if you have a circuit with the right properties, then you can solve these problems in polytime. Actually, everything I'm going to show you is going to be linear time, right? So once you get your Boolean formula in the right circuit form, you're basically done. And there is a lot of these. We're going to look at a few of them next, which gives us the gist of really what's going on computationally with these things. So the tractable Boolean circuits we're going to look at, they're all going to be based on negation normal form circuits. So these are circuits that have AND gates or gates. They have inverters. However, the inverters can only appear next to the inputs. So you cannot have an inverter after an AND or after an OR. So a layer of inputs or negated inputs, then followed by ANDs and OR layers, and no restrictions on fan-ins. This is not interesting on its own. In fact, if inverters were not at the input layer, you can always bring them there with at most doubling the size of the circuit. So this is not as interesting. What gets interesting when we start adding properties on these circuits, and then we start getting tractability. So let me start with the first property known as decomposability, which allows SAT to be solved in linear time on these circuits. Decomposability is very simple, and it applies to AND gates. It says for every AND gate, if you look at the subcircuits that feed into that AND gate, they cannot share variables. So if you look at the circuit here, this is over LK and this is over PA. They do not intersect. And this has to apply for every AND gate in the circuit. That's basically it. If you know how to take a Boolean formula and compile it into a decomposable negation normal form circuit, then you can solve SAT on that in linear time. These circuits are known as d-DNNF circuits. And by the way, I'm going to show this example quite a bit. It looks like a tree. It's not a tree. So if you see the variable p here, you see the variable p here. We're just not tying them for visual clarity, but it's a circuit. This is a circuit. Okay. So this is the first property. It's pretty simple. Now we're going to add another property that then allows us to actually solve MAJ-SAT and you know unlock the class PP. And this property applies to OR gates. And the idea is that regardless of what input you apply to the circuit, and in this case, red is high and blue is low. So regardless of what input you apply to the circuit, if you look at any OR gate like this, you're going to find at most one input is high. So in this case, there's only one high input, two low inputs. In this case, both inputs are low, that's fine, but at most one high input. And this would be true for any evaluation of the circuit. It's a mutual exclusiveness constraint. This is, if you look at this as alpha, and this is alpha 1, alpha 2, alpha 3, we want these alpha 1, alpha 2, alpha 3 to be mutually exclusive. And with another property called smoothness, I'm not gonna talk about it, which is easy to enforce, it's quadratic. You can do actually now counting and solve MAJ-SAT on these circuits in linear time if they're both decomposable and deterministic. So two simple properties, one on AND gates, one on OR gates. One unlocks NP, the other unlocks PP. And let's take a look at the concrete example first of really doing reasoning on these circuits before I introduce another circuit type. So let's say you have a circuit that has these properties, decomposable, deterministic, and smooth, and we want to count the models of the circuit. It's pretty simple. At the input, every literal, positive or negative, gets a count of 1. This represents false here, so it gets a count of 0. And you simply push upwards, adding at OR gates, multiplying at AND gates. That's basically it. And then you get this number 9, which tells you that 9 out of the 16 assignments are satisfying. It's that simple. In fact, there's a lot of algorithms on these circuits, and they all end up being just one pass over the circuit, doing a local operation at every gate, and then you get your numbers and your answers. You can do even more sophisticated things. For example, what we call marginal counts. So let's say you want to know how many satisfying assignments have A true and K false. Very similar procedure. The only difference is that these literals over these variables end up getting different numbers. I have to give this, you know, a 1 and not a 0 in this case. And this guy gets a 1 and K gets a 0. And then you just evaluate as before. And now you get the number 2, which tells you out of these 9 satisfying assignments, 2 of them have A equals true and not K equals to false. Pretty powerful stuff that you can do with this. You can do weighted model counting now, except that you passed in the weights instead of passing 1, 0 as before. And just you can see if you are able to get a circuit with this with these types, how much you can do with that. And realize that we've done here is basically multiplied at AND gates and added here. So really what's going on here, you can get rid of the Boolean circuit and use this instead. And these are what I called arithmetic circuits in this JACM paper. And they were introduced, in this case, you can think of these as compilations of probabilistic models. So you take a probabilistic model like a Bayesian network and compile it into an arithmetic circuit. I gave you one way of doing this here, but in this paper, this class of circuits is defined independently and semantically without this construction method. So there's 2 ways kind of to arrive at these guys. And there's a whole area now that is based on these arithmetic circuits in AI and machine learning. And realize that I can still talk about these properties of decomposability, determinism, and smoothness even on this arithmetic circuit because I didn't lose the structure of the variables. And again, you can treat and develop and study these somewhat independent of the construction method that I gave you. And doing marginal weighted model counting on this basically gives you marginal probabilities. So if you want to look at the picture, you have probabilistic model, you write a Boolean formula as we've seen, you compile that Boolean formula to a tractable Boolean circuit, get this arithmetic circuit, and now you're doing probabilistic computation in linear time, basically. And the only computational thing of substance here is the compilation of that Boolean formula to a Boolean circuit of the appropriate type. All right, let me do quickly another circuit type, which we're going to use it in the following segment. And what we're going to do now is we're going to strengthen the properties of decomposability and the properties of determinism. And then we're going to get an even more powerful circuit type. And the first one is structured decomposability, which is a stronger version of decomposability. Remember, decomposability said for AND gates, if you look at the subcircuits feeding into that, they cannot share variables. Structured decomposability says yes, but I want you to do that decomposition of variables in a structured way using something called a V-tree. A V-tree is just a binary tree, the leaves of which are our variables. So one-to-one correspondence between the leaves of that tree and our variables. And the idea is when you do the decomposition on an AND gate, it has to adhere to a particular V-tree node. So for example, this here adheres to that. What does that mean? If you look at the variables in the left subtree, it's LK, and then in the right subtree, it's PA, and that's what's happening here. And basically that's what's going on with these guys as well. So they're all adhering to this node and all splitting their variables in this fashion. And similarly recursively. So I cannot have those variables split differently than those. And that gives you more power, more computational. For example, the previous circuit types, you cannot take two of them and conjoin them in polynomial time to yield a circuit of the same type. But you can do it when you have structured decomposability, all right? So you get more power. And the last property I'm going to introduce here is known as partitioned determinism, which is a strengthening of the determinism property. And that leads to a circuit type known as SDD. Now it's pretty actually actively used in a number of areas. So what is partition determinism? These circuits are made of fragments look like this. You have an OR gate, and there's a bunch of AND gates feeding into it. Each has two inputs, and left and right matters here. So if we give names to these, G1, H1, G2, H2, G3, H3, and F, the requirement here is that these beyond decomposability and particular structured decomposability, the idea is for partition determinism, I want these G1, G2, G3 to form a partition. That is, for any circuit input, precisely one of them will be high and the others will be low. And what happens in that case, this fragment ends up working like a multiplexer. It's basically deciding which one of the H's to pass. So in this case, at these variables being all high, see this is low, and this is high. So what's happening is we're passing H2, all right? And you can see how that will give you determinism at this gate, but it's a stronger version of determinism. Now, why are these called decision diagrams? Because you can think of this as a decision node. It's trying to make a decision on which one to pass, this, or that. Now, why are they called sentential? Because this is in contrast to binary decision diagrams, the famous binary decision diagrams, which is a special case of this. We're going to see this on the next slide. But the point is, these guys allow you to solve MAJ-SAT, which is PP to the PP in linear time using an appropriate V-tree. So if you're able to compile your formula to one of these circuits, now you got PP to the PP and you can do expectations. And again, the beauty of all of this, all of these problems, probabilistic reasoning and machine learning, the essence of them is symbolic manipulations. I skipped over how do you do MAJ-SAT. That requires a circuit type called decision d-DNNF, which we don't have time for, but you'll see the references for that. All right, so let me just quickly show you this connection to binary decision diagrams. This is very, as you know, some people call this the most studied tractable representation of Boolean functions. This is how an OBDD looks like. it's a decision graph, and I give you variable instantiation and you want to know whether the function evaluates to 0 or 1, you simply follow the paths and see where you get there. And there's a requirement that these variables must be ordered on every path. Okay, what does this have to do with what we looked at? Well, this is the main ingredient of an OBDD. It's a decision node that looks like this. If X is true, go this way. If X is false, go that way. Well, that's nothing but this circuit fragment, which we just saw. The only difference is I only have two of these. One is conditioned on X and the other is not X. So we're making a binary decision. This pass this through or pass this through, depending on whether X is true or X is false. And SDDs basically allow you to partition over sentences, not just over variables. In fact, if you use a V3 that looks like this, what we call a right linear V3 or what's known as a right linear V3, and you compile an SDD for this kind of a V3, you get an OBDD. So OBDDs are a special case when using these kind of V3s. And in fact, you will see that if you do this partition determinism property that I mentioned ends up being nothing but Shannon's expansion, or what's known also as Boole's expansion. And interestingly enough, doing decisions based on sentences instead of variables leads to exponential reduction in size. So it's known that SDDs are exponentially more succinct than OBDDs due to this basic result. All right, so what I just talked about on tractable Boolean circuit in AI is studied under the area or what's known as the knowledge compilation map, where we look at circuits, various properties. When we put these properties on the circuits, what circuit types do we get? And people systematically study what operations become tractable under which properties. They also study the succinctness of these circuits, their relative sizes. The very first knowledge compilation map is actually about 2 decades old. Last year in France, there was a workshop dedicated to the subject, a full week workshop, and with applications, database theory, machine learning, and so on. And there is an up-to-date tutorial on knowledge compilation. This tutorial goes with the paper that or the stock with the paper that I just wrote to pods. It just appeared earlier this summer. And you will see all of the citations there for these. This slide is from this latest workshop, showing you some of the circuit types and the latest on the succinctness and what are the open questions and so on. So there's been quite a bit of interaction between this area of knowledge compilation and other areas. You see now titles, what I call them knowledge compilations meet X. Knowledge compilation meets database theory. Knowledge compilation meets communication complexity, meets uniform sampling. And some of the theory folks that traditionally studied OBDDs are also studying some of these circuits now. I'm going to finish this segment now. I didn't talk about the compilation process itself, which would be basically a rich subject, but I just want to mention the following. There are 2 ways to do this compilation, what's known as bottom-up compilation or what's known as top-down compilation. These kind of compilers, they work, let's say you want to compile a CNF, a conjunctive normal form. The way they do it is they take every clause and compile it individually, and they start conjoining these circuits. So this is similar to how OBDDs were originally proposed to be compiled in this seminal paper. You can do this for some of these like SDDs. And there is a tutorial on my YouTube channel. I'm going to give you a pointer to this later on this particular subject if you want to look into it more. The other approach is actually pretty interesting, top-down compilation. There are search algorithms that people have developed for, let's say, model counting. And they are based on DPLL, like depth first search and so on. And there's a whole variant of them. And what this paper showed that if you take these search algorithms and keep a trace, that is where you're going in the search, then that trace ends up being a circuit. So in fact, it showed that different variants on exhaustive DPLL algorithm produce different circuit types. So these compilers are based on search algorithms and then keeping traces. And this is the latest from our group that is based on that kind of paradigm. So let me see, what am I doing on time? Okay, I have, okay. I'm running out of time here. I'm gonna try to make this very brief, this section, and then go to the last part here, which is the most recent. The main idea of the second section is if you're learning distributions and you represent the probability space using a circuit, a tractable circuit, then things are great. And you'll see in what sense now. So let me use this motivating example here. So what I have here is data on 4 courses that students can take in a department. And what the data says is for each kind of course configuration, how many students did that. So this row says 54 students took this course and that course, but didn't take these 2 courses. So what I want to do is I want to learn the distribution from this data to reason about what students will do. Very classical machine learning problem, except in this case, I have constraints. I have additional input. I know that everybody must take at least one of probability or logic. Probability is a prerequisite for A and so on, which can be expressed using these logical constraints. So now I want to learn from both the data and the knowledge. And the way we propose to do this here is to take your domain constraints, which effectively define your probability space, and compile it into an SDD circuit. Why SDD circuit in particular? You'll have to go to the paper because it has the right properties. And now this Boolean circuit captured my probability space in the sense, if you give me any course configuration and you evaluate the circuit, if it gives you a 1, that means a legitimate. If it evaluates to 0, that means outside the probability space. Okay, but our goal is we want to learn a distribution over that space. And because of the properties of the SDD circuit, Boolean circuit, it turns out that inducing a distribution over the satisfying assignment of the circuit is very easy. All you have to do is give it this local distribution on every OR gate, on the inputs of the OR gate, all right? It's like this. So in this OR gate, we have 0.1, 0.3, 0.6. This OR gate, we have 0.6, 0.4, and so on. And these distributions are independent. There is no relation between them. You can assign them independently. And every time you assign a set of distributions, a local distribution to these OR gates, you induce a global distribution over the satisfying assignment, which has some very nice properties. I'm going to just review them quickly for you. But not only that, if you have data like this, and you want to find the maximum likelihood parameters, that is the parameters that will generate the distribution that maximizes this data, that you can do actually in closed form when the data is complete. Complete data means every row specify the value of every variable. So parameter estimation here, maximum likelihood parameter estimation, closed form, very nice. We won't have time to go over the semantics of these probabilistic circuits, but I will say it's compositional in the sense that every OR gate is its own little SDD that specifies its own distribution. And this whole circuit specifies this distribution over satisfying assignment to of the Boolean circuit. The distribution is always normalized regardless of how you assign the numbers, as long as these are normalized distribution, which is anyone who tried to invent representations like this, no, this is not easy. In fact, the distribution induced by this PSDD or probabilistic SDD circuit has properties that are independent of the parameters. So based on the Boolean circuit structure, you can write a bunch of properties that will always hold regardless of how you parameterize this. It's a very well-behaved representation. It is complete and canonical in some sense. It's tractable. You can compute MPE and marginals on this in linear time. I will just show you quickly now main application of this, or a couple of them, because you can do a lot more with this than what I just suggested. So here's, okay, so you do, there were some experimental results of various types out there showing what is the value of using knowledge in addition to data, which is what you would expect, that if you have knowledge, then you need less data. And these experiments compare this with other similar approaches that do not use knowledge, and you can see they need a lot more data to get certain properties. But let me quickly show you this because this is pretty interesting. You can use now this framework to induce distributions over combinatorial objects and learn distributions over combinatorial objects in a very systematic way with very little investment. at the conceptual level. So in this application, we wanted to learn distributions over routes. I'm going to use a toy example, but then I'm going to show you an actual application. You have a source and destination on a grid, let's say, and you want to look at the routes and you want to learn distributions over the possible routes from source to destination. You can do this easily by assigning a Boolean variable for every edge. And the idea is that a route is simply a variable instantiation. So these variables are turned on and everything else is turned off, but not quite, because this is a variable instantiation that doesn't correspond to a route. So what I want to do is, what you can do is you can write a Boolean formula over these variables whose satisfying assignments are only the valid routes. And they don't just have to be the connected ones. You can have additional properties like no cycles and da, da, da. The point is, if you take that Boolean formula and compile it to an SDD, you're in business. Now you're ready to start learning distributions over routes and reasoning with them. The idea is now this circuit, if you pass it a variable instantiation that corresponds to a true route, then you get a 1. If you pass it a variable instantiation that does not correspond to your combinatorial object, it gives you a 0. It captured your combinatorial space over which you want to define a distribution. And the only thing you had to do here, really, conceptually, is to write that Boolean formula that captures your combinatorial space. And the only thing you have to do computationally is just compile that formula, and you're in business. And here's another application. I'm going to get back to the routes in just a second, but we learned distributions over rankings, total orderings, and partial rankings, for which people have developed dedicated distributions. There's quite a bit of literature, for example, on distributions over total orderings. And the way to do it here is look how simple it is conceptually. In this case, we use n square Boolean variables. The idea is A21 means item 2 is in position 1, right? So I have n items and position, and when I say every position has exactly one item. Same story. This variable instantiation, these guys are true and everything else is false. They correspond to total ordering. This item is in this position, this item is in that position, and so on. This is a variable instantiation that does not correspond to a total ordering. This item appears in 2 positions. So again, you can write a Boolean formula. In this case, it's pretty easy. 2n constraints will have precisely truth assignments that corresponds to total ordering. You compile that into an SDD circuit. Now you're ready to start learning distributions over total orderings. In fact, we compared this to the Mallows model, which is a dedicated distribution for total orderings. Mallows is unimodal, is not competitive with this, but if you use mixtures of models, in this experiment, we had to go to about 20 mixtures so that that model ends up producing results comparable to what I just showed you here. And this framework doesn't know anything about total orderings except the Boolean formula that capture that combinatorial space. So for the routes, and with some advancements that I don't have time to talk about here, but they are mentioned in the extended version of this, we were able actually to compile almost San Francisco and some small countries. This is a map that has that many nodes, that many edges, and we were able to compile this into a PSDD and then use it to do things like, and then the data is actual GPS routes, actual drivers, what they took. And then we use this to do things like identify drivers based on what routes they took between a source and destination, and to do route completion. So you tell me someone is going from this place to that place. They've so far did this. What's the most likely way in which they will complete that route? All right, so this is, from a combinatorial point of view, this is a very, very substantial space, and you can use it using the systematic thing. I had a segment on supervised learning. I'm gonna skip this and go to the last part. Let me see, how much do I have? Okay, so I do have about 10 more minutes, right? Okay. This last part, so the first part been going on for 20 years. This is more like 6 years. This is more like the last 2 years, and pretty exciting. Let me just give you the gist of it, that on this slide, we want to compile machine learning systems. compile their input-output behaviors into tractable circuits so we can answer these questions, all right? And the idea is, once more, even though these machine learning systems are numeric and even though they're learned from data, their input is typically discrete and the output is discrete decision, which means that there are just sophisticated ways of specifying a discrete function. So we're going to capture that function using a discrete a Boolean circuit and then reason about it. Let me give you a concrete example. This is one of the simplest machine learning systems out there. It is a naive Bayes classifier, known as a naive Bayes classifier. I have features and I have a class variable. And typically I use this by, you give me a vector, feature vector, and I compute posterior over this, check over a threshold, render a decision. Well, that is a discrete function in this case because the inputs are these test results, in this case true, false, or they could be multi-valued. The output is a decision, yes, no. Right? So yes, the inside of the box is numeric and probabilistic computation, but input output, it's a discrete function. And we've showed in, so the root of this work is from 17 years ago, and most of the development is over the last few years. So 13 years ago, we showed that you can compile this guy into an OBDD. And in the sense that it will give you the exact input-output behavior. If you give me an instance like this, I just follow the OBDD, and in this case, the decision is no guaranteed. If you were to assert this instance as evidence here, compute the posterior, check against threshold, you're going to get the exact same decision, all right? And then the question became, what else can we do with this? What other machine learning systems? And what tractable symbolic representation? It doesn't have to be an OBDD circuit, could be some other type of circuit. And what can you do with these circuits when you get them? So over the last 2 years, we generalized from naive Bayes to tree structures and very recently to arbitrary Bayesian network classifiers, where we have algorithms that can compile them into decision graphs with some guarantees depending on the structure of the Bayesian network and so on. And later I'll show you, recently we've been looking at restricted types of neural networks, random forest, and so on. We're not gonna go over this compilation algorithm, but again, on my YouTube channel, you will see videos that go over some of these in detail. This lecture is just about the compilation of naive Bayes classifiers to OBDDs. But, and you'll see in some of our papers, all kind of case studies where we actually compiled classifiers from the literature. This was one of the classifier from Stanford Medical Informatics, actually, for breast cancer. And it's interesting what we found, that the size of the circuits vary from very small in some cases to very large. This particular guy, for example, had only an OBDD of 156 nodes. This is a Bayesian network classifier, numbers, learning from data, and the decision logic, excuse me, that it is implementing is simply this OBDD. You're seeing all of it here without labels of nodes, right? So I really abstracted, got rid of all of the numbers and gave you the essence, the decision function of that box here. So what can you do with these things when you get them? The first thing we looked at is explanation. And the idea is that we introduced one type of explanation, got better recently, which what we call the PI explanation, or sufficient reason. So the idea is you give me the box and you say, here's an instance, and then I give you a decision, yes. And you say, why did you make that decision? And what this explanation does is find a minimal subset of the instance that is sufficient to trigger the decision. So if you have 100 features, I may pick 7 of them and say these 7. As long as you have these 7, the decision will stick. It doesn't matter what the other 93 are. And we call this, in the original paper, PI explanation. Now we're referring to it more as a sufficient reason for the decision. And this notion is based on the well-known prime implicant notion from computer science and AI. You know about prime implicants. If you have a Boolean function, you're trying to find a minimal subset of variable settings that would trigger the function. In this case, there's 3 of them. If you make A true, B true, the function will trigger regardless of what C is. The PI explanation or sufficient reason is simply this. If you give me an instance and like this, and the decision is 1, you say, why did you make that decision? All you do is look at the prime implicants that are consistent with the instance, and those are the sufficient reasons. These are the minimal subsets of this instance that guarantees the decision to hold. If you have negative decision, you just work with the complement. Now, as you may know, one issue is that prime implicants could be exponential and therefore sufficient reasons. And sometimes you want to reason about the behavior of the machine learning system in a way that requires examining all sufficient reasons, and this becomes a problem. But luckily, you don't have to do this. I'll give you an example shortly and of new results, but let's just take a quick example here. So this is the classifier we looked at before. Sally tested negative for scanning blood and urine, and then the decision is she's not pregnant. And you say, why did you conclude that Sally is not pregnant? And the system will come back and say, because the scanning test and one of the blood and urine tests came out negative, right? This is the explanation. Why? Because where did this come from? There are two sufficient reasons for this decision. This is one of them, and this is the other. Scanning negative, blood negative, scanning negative, urine negative. If you take the disjunction of these, you get what we call the complete reason behind the decision, which is this statement. Now, realize we're doing this analysis on a machine learning system that is based on numbers, learned from data, probabilistic reasoning, and everything we're doing here is purely symbolic because we managed to first compile that machine learning system into a tractable Boolean circuit. A recent paper we just published a couple of weeks ago is dedicated to this notion of complete reason. It's a fundamental thing because it summarizes all of the sufficient reasons behind a decision. And the importance of it is sometimes you want to reason and examine all sufficient reasons, and this creature here allows you to avoid that. So this was the title of the paper, and it was focused on this, which is the disjunction of all sufficient reasons, again, to avoid computing all sufficient reasons. I'll show you an example next from decision bias, where you may have to examine every sufficient reason to answer a question, and this notion allows you not to do that. In this paper, we also showed how you can obtain the complete reason as a tractable circuit, which we call the reason circuit. So not only do I compile your machine learning system into a tractable circuit, when you make a decision and you say, why did you make that decision? I give you back another tractable circuit which summarizes why you made that decision. And let's look at an example from decision bias, all right? So this is a classifier for admission that was compiled into an OBDD. Here are the features. And decision bias is defined with respect to protected features. There is features that are not supposed to be used in making a decision. So the definition of, way we give the definition of a biased decision is the following. Decision on instance X is biased if it can be different on another instance Y that disagrees with X on protected features only. Remember, we're making a distinction between decision bias versus classifier bias. I'm talking about a specific decision. A classifier may be biased in general, but one particular decision it made may not have been biased. And one of the theorems in this work says, here's the importance. A decision is biased if and only if each of its sufficient reasons contains at least one protected feature. So this is an example of a query that in principle requires you to look at every sufficient reason of which we can have an exponential number. So it turns out with the new results, you don't have to do that. So here's an example. Robin is applicant. These are her characteristics. She was admitted by this classifier, and you say, why? If you look at the sufficient reasons, there are 5 of them. If I want to tell you, was this a biased decision, you would have to enumerate these and check them, but you don't have to. What we show in this paper is you can get a circuit, the reason circuit, which is equivalent to the disjunction of all of these in linear time, if the classifier is in the right tractable circuit, which includes OBDDs and another circuit type. So you give me the classifier and an instance, and you say, why was that decision made? I give you back another circuit that captures that. And this circuit ends up being monotone, so it's tractable. And you can use it to check whether the decision is biased or not efficiently. In this case, the decision is not biased. And the reason, if you look at these sufficient reasons, the protected features appears in only 3 of them, and the theorem says it has to appear in every one of them. And interestingly enough, in the paper, there is another theorem that says, oh, by the way, from this, I can tell you the decision, the classifier itself is biased. So even though this decision is not biased, it is guaranteed to make a biased decision on something else. What else can okay, the way these circuits are computed is very simple mechanically. They use a consensus operation, which generalizes the consensus operation on DNF. We're going to skip that, but it's pretty simple. I just want to tell you that you can do a lot more with these reason circuits. In the paper, this section is dedicated to a whole set of queries about the behavior of the machine learning system that can be obtained from the reason circuit. But just to whet your appetite and get you to read this paper, we can evaluate efficiently counterfactual statements like this one. We give semantics to statements like this one. This one says Susan, so Susan was admitted. And you can say Susan would still be admitted even if she did not have a high GPA because she passed the entrance exam and comes from a rich hometown. We give semantics for these even if because statements and show how to evaluate them based on the reason circuit. Sophisticated kind of reasoning, completely symbolically, because we were able to capture the input-output behavior of that classifier using a tractable Boolean circuit. Okay, so in a couple of minutes, I just want to say that you can also do things like do monotonicity of classifiers as another thing you can verify. I think this community knows what monotone functions and classifiers are. For example, on OBDDs, you can check monotonicity in quadratic time, and we've actually done some case studies on that. Initially, we started by focusing on explanations and then verification, and recently robustness. We started by graphical models, recently random forest and neural networks. We started initially by doing OBDDs as far as the target compilation. Now we do other things. This is an example of a small neural network we were able to compile, and you give it this image and it tells you this is a 0, and you say why, and what I showed you comes back with 3 pixels, says these 3. If these are white, this is always going to be classified as a 0, right? So, okay, I'm run out of time here, but robustness quickly is what is the smallest number of features you have to flip for the decision to change? That's how we defined it. And you can talk about instance robustness for a particular decision and instance, or you can do model robustness where you average over all instances. This is an example of a neural network. Also, we were able to compile 2 of them. And based on that, we were able to plot these graphs, which shows the distribution of robustness over instances. The 2 CNNs are almost the same in terms of accuracy, about 1% difference, less than 1%. One of them is significantly more robust. And this analysis is over that many instances, which was all done because it's compiled into tractable circuit. Okay, I'm gonna skip this unless people have a question later. We compile a very restricted type of neural networks. Input are discrete or Boolean with step activation functions, and recently we extended that to random forest. So just one remark here, and then the concluding slide. This segment is, I basically refer to it as reason about what was learned. A lot of these tools were originally developed to build the systems, AI systems are now being used to reason about AI systems that are not built using logic, but use machine learning. What I described to you is broader than what I mentioned. There's now a whole community, right? The formal verification community for VNNs, which does neural networks does similar things, but uses other tools like SAT solvers and so on. And this is focused on using tractable Boolean circuits. You probably scale more with these other tools, but you can get less because of typically they target NP, but it's pretty vibrant area now. And this is my concluding slide on these 3 roles, and the common thing between all of them, which is Boolean circuits, tractable Boolean circuits, basically cuts across through all of these. You can see the bots paper, which just appeared with the same title for references, and YouTube channel, just type UCLA Automated Reasoning Group, and you get our YouTube channel, and there's a lot of talks and tutorials on related subjects for people who might be interested. Thank you. I know I went over time a little bit, but this was a 2-hour thing that I put into 1 hour. Thank you.
Thank you.
Okay. Thank you, Adnan.
Sure.
Are there any questions from the audience? So you can either write them on the chat or raise your hand so you can ask to speak. Jean-François?
Yeah, I have some questions. So I like very much this idea of compiling, say, Bayesian networks or other classical tools from statistical methods to Boolean circuits. So can you say a few words on, because I mean, clearly the compilation may be exponential, right? Because those problems are complete for NP or higher. And so do you, I mean, for BDDs, for example, we usually take a description of Boolean programs, and then we compositionally compute a binary decision diagram by doing apply operation that you mentioned also. So is this the same kind of approach that you have here? And so in BDDs, for example, the variable ordering plays a very important role in the compactness. So do you have also, I mean, heuristics to
Right. So it varies on what system. The the compilation of Bayesian networks classifiers, the methods we have now are not like that, are actually top-down compilers. They do some kind of depth-first search in the space of variable instantiations, and they use some very sophisticated caching schemes. That's for the, at least the algorithms we currently have for the Bayesian network classifiers. However, for the neural network, where what we did is similar to what you do. I have the slides very simple. If you have, let's say the inputs are Boolean in this case, all right? And let's say you have a step activation functions. So both inputs are Boolean, step activation function, the output is Boolean. So even though the neuron looks like this, right? That's what the neuron is computing. These are the weights, and okay, that's actually a Boolean function. In fact, this guy is exactly this Boolean expression. So what we do first is compile each neuron into a corresponding Boolean function. Now, how do we do this part? The compiling naive Bayes classifiers to OBDDs, that's the same as this, because that algorithm actually works for any linear classifier, not just naive Bayes classifier. So we use that algorithm first to compile every neuron into a Boolean expression. And then if you take this little Boolean expression or circuit, plugged it in, now you have a Boolean circuit. You just converted the neural network to a Boolean circuit, equivalent Boolean circuit, by getting rid of the numbers. This now we compile using the apply, where we do bottom up and do the apply. And of course, these algorithms, if you're doing OBDDs, then you have to worry about the variable order. If you're doing SDDs, the V-tree plays the same role as the variable order, and it's the usual game, right? But that's this particular approach, right? But you could probably come up with, and this goes back to this bottom up versus top down. So you can think compilation methods. So you can think that our current methods for compiling Bayesian network classifiers are top down, while this one is bottom up, but there could be other ones as well.
Thanks.
Sure. But of course, let me say one thing. You can always fail.
Sure.
We scale more for Bayesian network classifiers because we invested more. We do very little with the neural networks. When I gave this tutorial at POTS, I ended up with a statement, which I'm going to end also mention here. I said, if you look at all of this, beautiful formulation, the bottleneck computationally all goes down to compiling a Boolean formula to a tractable circuit of the right size. And I said, people, work on compiling Boolean formula to tractable circuits. It's worth it, because the implications are just significant in terms of what you can immediately do now, right? I mean, we knew that we could do a lot, but if you look at the recent stuff for learning from data and knowledge or explanation or robustness, it's just fantastic. So it's really beneficial. The more we scale in terms of compiling Boolean formulas to tractable circuits, the more we can do.
Okay, thanks.
Sure.
Are there any other questions from the audience? Okay, so I had one, but it was basically the same question as Jean-François. So,
all right, very good.
I have other question if you want, but so for example, you mentioned sharp-SAT. So I do see that with sharp-SAT you can do, I mean, attack the PP problem, right? But so I mean, you can clearly do more when you have the circuit, right? Because then a lot of information is already pre-computed. So can you say something about the performances of the two approach? Or
well, so this year there was an first evaluation of model counting and weighted model counting.
Mm-hmm.
And so you could go and use a dedicated algorithm for counting, or you can compile into circuits.
Mm-hmm.
So our C2D compiler, which does model counting by compiling into a circuit, deterministic, decomposable,
mm-hmm.
actually was the first, solved the largest number of problems. There was weighted model counting. Another solver from a group of Pierre Marquis in France for weighted model counting, which is similar. It compiles circuits, was the first. Shared with another group, I think Moshe Vardi
mm-hmm.
Tied with that. So the two top model counters for model counting and weighted model countings are knowledge compilers.
I see. But so, for example, if you look at SharpSat, there are also natural approximation problems.
Okay, approximation is another story. This is all exact. When you go into the world of approximation, and this competition did have an approximation version of it, but I'm talking about exact.
Yes.
The beauty, let me tell you, the beauty about compiling into circuits, also theoretically. So when we showed that you can take model counters, the ones that do search, and that their traces are circuits, now you can you establish lower bounds. So if you, because of what we know about the succinctness of circuits, mm-hmm. So if you tell me I'm using this model counter based on search, and I know that its traces belong to a particular circuit, then now I can tell you a lot about its performance based on what we know on circuits. So it's not just a practical way of building compilers, but it also gave us a way to prove properties of some of these algorithms. But once you get the circuit, it's just, you saw like you do marginal counts. I didn't show you, but if you do one pass on the circuit, you get the model count. You can do another backward pass on the circuit to compute the derivatives of the output with respect to the inputs. Mm-hmm. And those are all marginal counts. So you can get an n counts by one pass over the circuit. You can do some very sophisticated things once. And again, look at the current competition. The two for model counting, weighted model counting, are based on circuit compilations, top performers. The other, I should mention D4. D4 is the knowledge compiler from Pierre Marquis' group, from Krill, from Lans, I believe, and the other one is C2D from our group. In the POTS paper, you'll find the citations for all of these systems and tools.
Okay, very good. Thanks.
Okay.
All right. Thank you, everyone. It was a pleasure.
Once again, it was a pleasure to have you with us. Okay, we are.
All right. So I guess. Okay. Bye-bye.
Thank you.
I don't know what the format is. It's very early in the morning here, so.
Yeah, we will have a technical session now on paper that have been accepted to.
Oh, okay.
And it will be about quantitative games, if I remember well.
All right. Okay. Very good.
So, yeah.
Okay, guys. Thank you again. Thanks everyone.
Thank you. Bye-bye.
Bye-bye. I'm gonna stop.